Yeah, the point was that, so what I was saying last time was, if you take this equation, u gather equal to 1, and it's a, I mean, we're talking about 2 cross 2 matrices, right? So let's call the elements as Z1, Z2, Z3, Z4. Say u is that. Then you plug that in this equation, it will become quadratic in these variables, no? Because, yeah, I mean, so u dagger then is Z1 bar, Z3 bar, Z2 bar, Z4 bar. And then you take the product of this. So this left hand side is Z1 bar plus Z2 Z2 bar. Okay, that's the first element. And then you have Z1 Z3 bar plus Z2 Z4 bar, etc. Right? And this is supposed to be equal to 1, 0, 0, 1. Right? Now what we want to do is we want to solve for this. These are the unknown quantities, right? We want to solve them to determine what's the most general form of the u, right? But to solve that is not so easy because these are quadratic, right? I mean, this is equal to 1. Quadratic in the original variable. So that's all. It's, yeah, but then what we did was we used various tricks and we found that this whole thing finally boils down to just one equation. Right? Finally, one equation which you needed to solve. I mean, the other things were determined, right? So, what was that? Right, so we found that also the determinant condition which m equal to 1, this condition basically says that the determinant is Z1, Z4 minus Z2, Z3, and this is equal to 1. So this is also a nonlinear equation, quadratic. I mean, it's quadratic in these variables, right? And then we found that the solution was this Z4, Z1 was equal to Z4 bar, and
Z2 is equal to Z3 bar.
Sorry? Okay. Yeah. We found the solutions, and then when you plug that back in here, and then we found that the determinant condition was simply that. Okay. So the final solution was, this was just Z1 bar, and Z3 was minus Z2 bar. Right? So now we have only 2 complex numbers, and these 2 complex numbers satisfy this equation. So any Z1, Z2 will satisfy that equation, and you plug those Z1 and Z2 here, then the matrix U is a unitary matrix and determinant is 1. Right? So if everything is satisfied. Okay. And then we found that this equation geometrically had a meaning. Geometrically, it just gives you an S3, 3-dimensional sphere. So that was the. Okay. Then we started talking about the infinitesimal generators. Okay. Now this is, you should pay really a lot of attention to this, because in fact in the rest of the course we'll be talking about basically generators. Not so much about the group. Only in this chapter we'll be talking a little about the group, but from next lecture onwards, or maybe after 2 lectures, we'll be almost entirely talking about the generators. Because generators have, I mean, really very rich structure. And you can learn almost everything about the group. Not everything, but almost everything about the group. Right. So we found that we looked at this infinitesimal generators. So elements which are very close to identity. Okay. So elements, so the U, which is very close to identity. Identity is just identity matrix, plus some epsilon times, I think what was the symbol we were using? I think you were just calling M, yeah? M. Okay. Plus higher numbers. Okay. And then, of course, it becomes immediately that it seems U dagger. So U dagger will be identity plus epsilon M dagger plus, again, order epsilon square. Okay. This is again some matrix, but we are not interested in that. Huh? We are only looking at the linear term, first order M epsilon. Okay. And then, suddenly the U dagger U equation becomes very simple equation, because this is nothing else but, so if you take the product of these two, the 0th order term will be simply this times that, the 0th order in epsilon. And the first order term in epsilon simply will be this times that plus this times that. Right? But identity times any matrix is again the same matrix. So you just get M plus M dagger. And then everything is higher order. Because the product of these two will give me epsilon square, and also epsilon square will come from there. So all that is order epsilon square. And now you see this equation is very simple. It is simply M dagger equal to minus M. So if you write the matrix M as some matrix, I don't know, let's call it x1, x2, x3, and x4. These are complex numbers. I mean, okay, maybe I should. I'm not using Z because Z we were using for the group element. Okay. But these are complex numbers in general. Then this equation is immediately you can solve because just linear equations. Right? So at the level of generators, the calculation becomes very simple. So yeah, and then from here, we found that the most general M can, of course, sorry, there's one more condition, determinant of U equal to 1. But determinant of U, if you expand in orders of epsilon, was simply 1, I mean the 1 plus the trace of U. Epsilon times trace of U, plus order epsilon square. This we went through last time in detail. So determinant equal to 1 condition tells me that to the first order, trace of M must be 0. Okay. So we have this condition and the condition that trace of M is 0. This is for SU2. If you had U2 on the other hand, then there is no condition here. Okay. The determinant could be anything. But for the SU2 case, we have both these conditions. And then from here, we found that you can, the most general such M can be expressed in terms of the Pauli matrices. I, say, XA, sigma. Where sigma Pauli matrices where sigma 1 was equal to 0, 1, 1, 0. Sigma 2 was equal to 0 minus I 0, and sigma 3 was equal to 1, 0, 0, okay. Note that these are all Hermitian, right? Because this kind of anti-Hermitian, sorry, I. There is an I here. So when you take M dagger, this I will pick up a minus sign because you have to take complex conjugate. XA are real. I should have mentioned that. XA are real. Okay, and so there's a minus sign, so that minus sign takes care of that. Okay, then you have just the condition that sigmas, XA are real, so nothing happens. So sigma must be Hermitian. Okay, and indeed you can see that all the matrices are Hermitian. Yeah, and secondly, we have the condition trace of n equal to 0. That means we have to also make sure that the traces of these guys are 0, and that's also true. The trace of all of these matrices are 0. If you did not have the trace condition, so this was the trace condition, yeah? If you did not have, so suppose we are looking at U2, so no trace condition. In that case, I could add to this one more matrix, and that is the identity matrix, or I times identity. Right? So I times 1 is 1, 1 is 0. No, I has been already included, so I don't need to worry about that. So 1, 0, 0. So in that case, you see, you could have also put that. No? So if it was U2, then you'll have one more term, which would be I times, let's call it x0. So let me put here plus I times x0 plus the identity matrix. That's the identity matrix. Okay. this would be if you have U2, if you're looking at U2. If you're looking at U2, you have this plus that. But if you're looking at SU2, then this is not there. So that's it. And now you can also count the dimensions. I mean, how many, like we saw that in at the level of group, SU2 was a S3. S3 has 3 atoms, right? Just like S2, any point on S2, you need to you define by giving the 2 angles, right? The azimuthal and the axial angle, whatever it's called, right? Theta and phi, 2 angles. Same way for S3, you will need 3 angles. So it will be 3 dimensional. Or you could, even without talking about the angles, you could see that S3 equation for S3 was x1 square plus x2 square plus x3 square plus x4 square. Again, this x has nothing to do with that x. I mean, okay, maybe I should have used some other letters here. Equal to 1. And you see this equation basically says that out of 4 real variables, you can fix one of them, right? So what is free are 3 variables. So that is the dimension of the space. So that was at the level of S3, but this was, you see, much more difficult because we had to really go through a rather complicated process to determine even this equation, that you have z1 square plus z2 square equal to 1, z1 mod square plus z2 mod square equal to 1. There was a little bit, okay, SU2 was still very simple, but you can imagine if you go to SU3 and higher matrices, it will become extremely complicated to solve them. On the other hand, generators is very trivial. To solve for the generators is very trivial. You see, just a linear equation, you can get that. But of course, the counting has to be the same. The dimension of this space must be the same as the dimension, as the number of infinitesimal deformations you can make. You know, from identity, you're starting from identity because everything is starting from identity. We are writing identity plus a small epsilon times some matrix. If the space is 3-dimensional, we should have 3 parameter family of these matrices, right? Because if the dimension is, say, suppose dimension is 2, you are sitting at one point. There are all these possible ways you can move, no? From that point, little bit move around. So that is in two-dimensional way. So there are 2 parameters involved in that. I can move in, say, in one direction, a little bit, and a little bit in another direction. So you need to specify 2 parameters if you're talking about 2-dimension. If you're talking about 3-dimension, you need to specify 3 parameters, right? So that counting immediately works out here. You see, this XA, there are exactly 3 of them, right? Because there are 3 polymatrices. So the number of coefficients that you require to specify M is exactly 3, which is the dimension of the group. So that's so this is a very general feature. This is not just for SU2, but for everything that we'll be discussing. Okay. And then we saw, so these are the polymatrices, and yeah, I think we stopped there last time, right? We didn't go beyond this last time. No.
We have reached the tangent space.
Sorry?
The last topic was the tangent space. We were going to start.
We're going to talk about tangent, yeah, tangent space.
But I have a question, Professor.
Yeah.
In S3, we have 4 dimensions, but we only have 3 parameters, right?
Yeah.
So not always the number of dimensions equal to the number of parameters.
No. This is not. This is only for U2. This extra term is not allowed for SU2, right? Because the trace is not 0 here.
Yes.
So this is not allowed for SU2. For SU2. Okay. For U2 is allowed, but that's not a problem because we know already that if you take a matrix of SU2 matrix, then you can, from there you can construct a U2 matrix by just multiplying it by a phase. Yeah. So any SU2 matrix, let's say if you just multiply by some arbitrary complex phase, arbitrary phase, this will be a U2 matrix if theta is not equal to 0 or 2 pi. This is the U2 matrix. So that's extra parameter there. That parameter is that x0. X0 is that theta. Okay. So yeah, for the U2 you will have that extra. And that is nothing else but just this guy. Because you see, after all, you're writing when you go to the infinitesimal level, you're writing this as identity plus epsilon n, that u, but e to the I theta also, because the identity is when theta equal to 0, right? So you should write it as e to the power of I 0 plus epsilon theta. So because 0 is the e to the, I mean this should be 1, and that's identity. That is when it becomes identity, right? So you have this. So when you expand, so of course you will get, so when you expand it, you will get 1. So this one is nothing else but 1 plus I epsilon theta, and you're multiplying this 1 plus epsilon n, I mean identity. I always write the, I mean many times I forget it, but I try to write 2 lines to indicate that it's a matrix identity, no? Not number 1, just to distinguish between them. But sometimes I forget it. So if you now open this up, this is a number, and you're multiplying this number to this, both are matrices here. So first 1 times 1 of course is identity, 1 times identity is identity, plus this times that, so you get here I epsilon theta times identity, and then you have this times that, which will be epsilon n. Okay? So you get this extra piece, which is again linear at epsilon, plus higher order, plus order epsilon square and not writing down. Okay? And that's exactly that we see. So this is a theta, x naught is a small theta. Okay, so the point about this tangent space is to give you a feeling of the geometry. I mean, what are we doing here? Huh? So, okay, I will not spend too much time on that, but just very quick. I should say I am lagging behind. I should have finished this chapter last week, so I'm a bit going behind. All right, so the idea is the following. I mean, if you take any, so take an example. Let's say S1. So this is the U1. U1 is remember U1 was S1. The space was a S1, just the angle theta. Okay, because we can visualize it here. Otherwise, I mean, to draw even you cannot even draw on the blackboard. S3 you cannot even draw. No? So just to get a feeling for that. So what is the tangent space? I mean, so this circle is say x square plus y square equal to 1. Yeah? So here is my x-axis and that's the y-axis. Origin is the center is at the origin. So y. You can all see, hear me well, right? Now?
Yes, sir.
Okay. Okay. So now suppose I take, I start at some point, x naught, y naught, which is on the circle, so which means it satisfies this equation. Okay. Now look at what is the tangent. So at this point you can draw two special lines. One is what is called, so this is a radial direction. Just draw a straight line from the origin. Clearly this, if you and the tangent direction, that's a tangent direction. Okay. These two are perpendicular to each other. Okay. That's a radial direction and that's a tangential direction. Okay. So what is the meaning of tangential direction? Tangential direction basically says that if I think of, let's see, how shall I say? You want to ask the following question. I mean, in what direction I can move such that x squared plus y squared remains 1. Okay. In other words, let's look at deformation. I mean, small change in the x. So we are sitting at x naught, y naught. So let's write x equal to x naught plus delta x. A small change. And similarly, go to the, so we are sitting at y naught plus again delta y. So we are looking at some point near this point. Okay. So some point, let's say here, which has this coordinate, x naught plus delta x, y naught plus delta y. Okay. Now we want to ask the question, what is the condition that actually this point is on the circle itself, not outside the circle? not the x0, y0, but some neighboring point on the circle. And so for that, I just have to plug in this equation, right? So I plug that in the equation and check what is it, what it is. X0 plus delta x squared plus y0 plus delta y squared. Let's open this up, and again we'll keep only up to the first order. So imagine I have put an epsilon here, and I just want to keep epsilon, linear term in epsilon, not epsilon squared. Throw that out. Right? So this will become x0 squared plus 2 x0 delta x. Okay. And plus delta, again, as I said, I'm not going to, linearize delta x squared plus y0 squared plus 2 y0 delta y plus delta y squared. Okay. And I will forget about that because I'm thinking of very, very small. These are very small. And this has, so the question is it equal to 1? Or is it different from 1? Right? If this new point is again on the circle, then it should satisfy, then it should be equal to 1. Right? But if it is not 1, then okay, it's a little bit out of the circle. But okay, x0 squared plus y0 squared is already 1 because we assume that the starting point was on the circle. So this is already equal to 1, so that 1 cancels with this one. Then the equation we get is simply x0 delta x plus y0 delta y equal to 0. So that's the equation we can find. That is the condition that this infinitesimal change still sits on the circle. Right? The new point is still on the circle. Now, if you look at this equation, what does it tell you? You see, what is the vector? This radial vector. The radial vector is this direction, right? Its components along the left, along the x and y axis are simply x0, y0, right? This vector is simply given by is the x0, y0. Right? This vector. Let's call this vector v. Let me just call it. Okay, let's call it. Okay, let's just call it v. So v is this vector, right? The vector v, its x component is x0 and y component is y0 because this point is x0, y0. Okay. Now this equation I can write it as v dotted with delta x delta y equal to 0, right? I mean dot product, the vector space there is dot product, right? If I have two-dimensional vectors, the dot product simply means multiply the first components of both the vectors plus multiply the second component of both the things, right? This is a dot product. So this equation can be written in this language. It's the same equation, right? Because this is v is x0, y0. So this dot product is nothing else but x0 times delta x plus y0 times delta y. And that's equal to 0. So this tells us that actually this vector must be perpendicular to that vector, right? Because if there are two vectors whose dot products are 0, then they must be perpendicular to each other, right? So this was the direction for the v, and the direction that we are, by demanding that the infinitesimal change stays on the circle, is just saying that this delta x delta y is actually defines a vector which is perpendicular to that vector. So that is what it means that. So we are looking at the tangent direction. This is tangent to this curve. This direction is a tangent to the curve, right? At that point, x0, y0. Of course, this tangent will change. I mean, if x0, y0 was here, then the tangent will be this direction, right? So what is the tangent will depend on the original point you choose, but whatever it is just tangent to this curve. That is a yeah. Okay. And in fact, this equation also I can write it in a slightly different way. Let's call this function as f of x, right? Function is x squared plus y squared. So this is just x squared plus y squared. So this equation I can write it as df by dx evaluated at x naught times delta x plus df over dy evaluated at x naught y naught, whichever the point you're looking at, that's equal to 0. That's equal to 0. Sorry, delta y equal to 0. So that's the equation. So what is the meaning of that? It is just saying that the delta x, delta y, this vector, let's call this, give some name to that. This vector is, as we said, is a tangent vector. So let me use a t for the tangent. So this equation is nothing else but the directional derivative, dA df over dxa, evaluated at x naught, y naught, equal to 0. So it's saying the directional derivative of f along this vector is 0. But that's exactly what we did before, right? We said which direction I can move so that this quantity doesn't change, right? The change in this quantity is exactly that. I mean, if I just take t to be any arbitrary vector, you ask the question, if I take a directional derivative, if I move along that direction, how much this f changes, right? In general, it will change. In general, it will change for any arbitrary direction. But the tangent direction is the one where this function this f doesn't change to the first order, infinitesimal level. So now, I mean, it's clear now. I mean, so here was one-dimensional thing, but now it's hard to draw it. But imagine I have a two-dimensional sphere. Okay, I have a two-dimensional sphere. Again, it's difficult to draw. I mean, you imagine it's a sphere. Okay, and you sit at some point. How can you draw it? I mean, you know, I sit at some point there. Now, what are the? Okay, let's say I even sit at one point here. Now, from here, you can go in various directions. I can go in this way. It doesn't change. You are still on this on S2. Or you can go in the azimuthal angle. No? I mean, think of this as a, I don't know, this is a S2. Okay? There is a north pole, south pole, and your center is here. This angle is theta, and this angle is the phi. So imagine the globe. Now you're sitting at this point. So what are the possible ways you can go infinitesimally, staying on the surface of the sphere? Right? There are two independent ways. I can go this way, or I can go along the azimuthal angle, and of course any linear combination of them. These are vectors. You know, you can take any linear combination of them. You can go in any direction in this two-dimensional space, the surface. No? You're sitting on the surface, and you can go in different directions. So the tangent space in this case will be a two-dimensional space, right? And once again, it's the same idea. You'll have now the equation x squared plus y squared plus z squared equal to 1. Okay, and then you will have the similar condition. You'll have x naught, y naught. I mean delta x, delta y, delta z, and you will get in that case. In this case, you will get so we have x squared plus y squared plus z squared equal to 1, and you look at again. X plus x naught, I mean say x naught plus delta x, y naught plus delta y, and z naught plus delta z. And you want to ask the question, what is the condition on delta x, delta y, delta z, such that it is still on the sphere? No? And what you will find basically the same thing, x naught delta x plus y naught delta y plus z naught delta z equal to 0. So these are all the directions which are perpendicular to the radial direction. See, radial direction has the components exactly x naught, y naught, and z naught. Right? So this is just saying that delta x, delta y, delta z is a vector which is orthogonal to the radial vector. So that's a tangent relation, tangent space, tangent to the surface. And of course, this equation will, you see, it's one equation for 3 real numbers. X0, Y0, Z0 I have fixed already. So that I'm not free to move, right? I'm just sitting there. But delta X, delta Y, delta Z are arbitrary. That's what we want to determine. There is one equation for 3 unknowns. So there will be two parameter family of solutions. That 2 parameter family of solution is exactly the 2-dimensional tangent space. That defines a 2-dimensional tangent space. So, right. So now, coming back to our 3-dimensional, okay, again, S3 also the same phenomenon. For SU2, it will be the same thing. You'll have now, I don't know, you'll have for SU3, where the space is S3, you'll have plus, say, W0 square. So it's a 4-dimensional, you start with a 4-dimensional space and you put this constraint, right? So now it will be, you'll have W0 plus delta W. Okay. So then on this side you will have an equation W0 delta W. That's equal to 0. Okay. You cannot visualize it, but X0, Y0, Z0, W0 is the radial direction for the S4. Right? And this is again, this just tells you that this delta X, delta Y, delta Z, delta W, which defines a vector in 4-dimensional space, has to satisfy that condition, which means it's orthogonal to the radial direction. Radial direction being X0, Y0, Z0, W0. So this is the same situation. But now let's go back to the generators. What are we doing? I mean, if for generator, we are saying that we're not looking at an arbitrary, like here I just looked at an arbitrary point, X0, Y0. No, there we are looking at identity. We want to expand around identity. Identity is just one special point on the S3. No? It's just one special point on S3. And if you parameterize, I think this parameterization probably I never wrote it for you. Yeah. So actually we did that. So remember the SU2 matrix was Z1, Z2 minus Z2 bar, Z1 bar. And we wrote Z1 equal to X1 plus IX2 and Z2 equal to X3 plus IX4. And you remember this had a condition that Z1 mod square plus Z2 mod square equal to 1. Right? That was a condition for this to be SU2. Okay? And so we just wrote Z1, Z2 are complex, so I can always write it like this. Then this equation simply became x1 square plus x2 square plus x3 square plus x4 square equal to 1. Okay. Now, so that means we said every element of this, every matrix, every such matrix is a point on S3. But when we talk about generators, we are talking about a special point. And that special point is an identity, identity of the group. So what is the identity of the group? Identity of the group, identity is simply the unit matrix. Right? So the question is, for what value? I mean, so this tells me that Z1 equal to 1. So this means Z1 equal to 1 and Z2 equal to 0. Right? If you look at, if you just compare this, that's a special point in this sphere. But Z1 equal to 1 means X1 equal to 1 and X2 equal to 0. Because Z1 was X1 plus IX2. And Z2 equal to 0 means X3 and X4 are also 0. So that's a particular point on the sphere, on the S3, where, let's say, I don't know, you can think of it as a north pole, say, of the S3. S3, you cannot visualize, I mean, on a globe, at S2 you would talk about a north pole, right? But see, imagine something similar. So this is one particular point, and we want to expand around there. Okay? So when I expand around there, so do the same thing here. So we have now, we just take the special case where x0, this is equal to 1, and everything else is 0. I mean, think of this as x1 not, I mean x1, x2, x3, x4. Unfortunately, I changed this notation. I mean, is that clear to you? I mean, just call x0 as x1. I mean, x as x1, y as x2, z as x3, and w as x4. And so we are expanding around x equal to 1, y equal to 0, z equal x2 equal to 0, z equal to 0, and w equal to 0. Like, why not exchange it to write it like this? I mean, x1 naught, x2 naught, x3 naught, and x4 naught. Okay. So this is x1 naught, which is 1. This is x2 naught, which is 0. And this is x3 naught, which is again 0. And x4 naught, which is again 0. And then the equation became, so it was, when you take the square of this, I mean square of this plus square of this plus square of that, etc. You see the first order term only appears here, right? Take the square of that, it will be 1 plus delta, 1 plus, this is 1, right? This value is 1. So 1 plus delta x square, which is 1 plus 2 delta x, plus delta x square, which we throw away. But here, since this is 0, square of that is already second order, delta y square. So you throw that out, right? Here again, this is 0, so it becomes delta z square, which is you throw away, and here same thing happens here. So this whole thing becomes, if you restrict to the first order in the small variation, then it's just 1 plus 2 delta x, and that's equal to 1. So this x1, since I'm calling it x1, x1, x2, etc. So delta x1, so this just tells me delta x1 is 0. That's it. Sorry, did I confuse you with all this notation changes? Is everything clear to everyone? Yeah. Okay, so that's all the conditions. So now I'll look back at this matrix. So this matrix now, once we substitute this here, this was x1 plus ix2. This is x3 plus ix4. And this one is minus z2 bar, so it's minus x3 plus ix4. And z1 bar, which is x1 minus ix2. Okay. Okay. Now we just look at this. We add this small change, and then we see that the small change delta x1 has to be equal to 1, right? So first of all, we said that so this becomes the delta x1. So let me write delta once. This delta x. So we are saying that all of these guys have 0, delta x2, delta, only the condition is delta x1 is 0. That's the only condition. So if I put delta x1 equal to 0, so set delta x1 equal to 0, that is what the condition comes from. And then the most general matrix is I delta x2 times 1, 0, 0 minus 1 plus look at the coefficient of delta x3, 1 minus 1. So let me put it like this. Okay. Let's write it like, since I want to take out an I, that's just a matter of writing. I delta x3 times, if I take out I from here, then it should be minus I here, 0, 0. And then finally the last one, the delta x4 plus I delta x4, and you get 1 and 1 here, 0, 1. Okay. So you see that immediately you see the Pauli matrices appearing here, right? So the interpretation of the generators is nothing else but you're looking at the tangent space, but not at any arbitrary point. Tangent space at the identity. Okay? So not just any arbitrary point, it's identity. But you can use all the structure. This clearly is a vector space, as we saw in all these examples. So in the, this, if you look at the small changes, linear, I mean the first order changes, then they form a vector space, right? So this also forms a vector space. Because indeed you can take this, say one such element, and you can add another one, delta x2 prime, delta x3 prime to this, that will still be a generator, right? I mean, to add to this another one. So I delta x2 prime times the same matrix plus I delta x3 prime plus I delta x4 prime. Right? You can add them and they are still generated, right? They still satisfy the same conditions. So you can add them. So that's a vector space. That's very important to understand. That group space is not a vector space. But the generators is a vector space. You can add, if you're given two generators, you can add them and you have, again, that's a generator. This goes back to the statement that at the level of generators, the equations were linear, right? At the level of group, the equation for SU2 was a quadratic, I mean, the nonlinear equation. But at the level of generators, the equation became linear. So if I find one solution and you find another solution, clearly when I can add them up, that will give me a solution, right? So that's why it's a vector space. That's very important to do this. That's why the study of generators becomes much easier, because vector space we can do a lot. But that's the reason. Of course, if it was just easier, but it didn't capture much information, it wouldn't be very useful, right? But it turns out that this captures a lot of information. This in the context of these generators, and that is what I wanted to say now. That the generators are not only vector space, but there is one very important structure. And I will just mention it now, but I will describe it a little bit more detail later, after starting to talk about SO3. But I will just say what it is. Okay. So again, let's go back to the polymatrices, sigma 1, sigma 2, sigma 3. Now this, I think you have all seen these things. If you take the product of these two polymatrices, in general, I will just write down the formula. You can check that sigma A, okay, let's write. So first of all, sigma 1 square equal to sigma 2 square equal to sigma 3 square equal to 1. One meaning identity. 2 by 2 matrix. Let me just write it down, the sigma again. 1, 1, 0, because sigma 1, sigma 2 is 0 minus I 0, and sigma 3 is 1, 0, 0. You can immediately check sigma 1 square is identity, sigma 2 square is identity, and sigma 3 square is identity. What about when they're two different things? Sigma 1, sigma 2, you can show that this is nothing else. Let's multiply that. So you get here, so this is, it becomes I sigma 3. Let's just check that. Let's see if it's true. So 0, 1 times this guy gives you, I'm multiplying this with that, in this order. Yeah? The order is very important here, because matrix multiplication is not commutative. No? So you have to keep track of the order. So that's important. So sigma 1 times sigma 2, you multiply this with that, so you get here I, that with that is 0, this with that is 0, and finally this with that is minus I, which is nothing else but I sigma 2. Okay. And so on, you can prove, you can look at sigma 2, sigma 3, that's equal to I sigma 1, and sigma 3, sigma 1 equal to I sigma 2. What if you had done the other way around? Suppose I had done not sigma 1, sigma 2, but sigma 2, sigma 1. So multiplying the different opposite order, not this order, but other order. So in this case, you multiply. Let's do that again. This with that, so this gives you minus I. So you see this with that. This with that is 0. This with that is 0, and finally this with that is I. You see, this is the minus of that. Okay? So this was, remember, this was sigma 1, sigma 2. But sigma 2, sigma 1 is just the minus of that. So what we are seeing is that sigma 2, sigma 1 is minus I sigma 3. And similarly, you can check for all the other ones. Sigma 3, sigma 2 is, so let me just write down. This happens to be also equal to minus sigma 2, sigma 1. This happens to be minus sigma 3, sigma 2. And this is same as minus sigma 1, sigma 2. So that's a rather interesting algebra here. So in general, I can summarize these things as writing it as sigma A, sigma B is equal to delta AB times identity. Because you see, whenever the A and B are equal, you have these equations, right? That's identity. Plus I epsilon ABC sigma C. Okay? Where epsilon ABC is epsilon 1, 2, 3 is plus 1. Okay, and it's antisymmetric. I mean, every time you exchange two positions, you pick up a minus sign. Okay, this is totally antisymmetric. This is a Levi-Civita, in case you have heard about it, Levi-Civita sigma. Totally, that is totally antisymmetric. Any pair you exchange, it picks up a minus sign. So for example, if I exchange 3 and 1, that means epsilon 3, 2, 1, it would be minus 1. So this is the definition. This defines completely this epsilon. So this is a very interesting thing that this polymatrices satisfy. Actually, this is kind of an accident. I mean, this doesn't happen for higher groups. This is a very special case for SU2. That there is such a simple relation. However, there is something which, from this equation, suppose I take the commutator, sigma A, sigma, please check it, in case you have not, I'm sure you have seen it already in your courses, no? But in case you have not seen it, please go through this calculation just to check it. Sigma A, sigma B, commutator, there's a notion of a commutator. So I put here, so in general, a commutator of two matrices, X and Y, is by definition, this is X times Y minus Y times X. Okay? That's the commutator. This is called the commutator. This operation is called the commutator. So from this equation, then it follows that if you take the commutator, so which means sigma A, sigma B minus sigma B, sigma A. But you see, when you take difference, sigma A, sigma B minus sigma B, sigma A, this cancels. This goes out, right? Okay, but that doesn't, because AB, BA, this picks up a sign, right? So when you subtract, I mean, what I'm saying is that sigma B, sigma A is equal to delta AB, I. This doesn't change. But here, it should have been I epsilon BAC, right? Sigma C, because this is for any A and B. So I just call this A, B, and that A, then this should become B and A. But now I use the fact that epsilon is totally antisymmetric. So I can rewrite this as AB and change the sign. Okay. Now I take the difference between these two, this minus that. That is what is the commutator. So this is sigma A, sigma B, minus sigma B, sigma A. And you see that this cancels, but this doesn't. This adds up when you take the difference. And you get simply 2I epsilon ABC, sigma C. Okay, this is very interesting. You see, what it means is that you started with the two Lie algebra elements. Sorry, let me not call it Lie algebra, I'm jumping ahead. Two generators. These were all generators, right? Okay. I mean, we were calling the generators I times sigma, but it doesn't matter. You can multiply everything by I. So there will be some signs will change and so on and so forth. But the basic point is that generators can be expressed in terms of these polymatrices. Okay. So we have these two generators, and I have an operation here, which I call commutator. On the right hand side, you again get a generator. Okay. This is very interesting. Yeah? So there is some, so first of all, what we are learning from this is that not only that the generator is forms a vector space, but there is another operation in there. which is called the commutator, in such a way that the commutator operation, given a pair of elements of the generators, two generators, a commutator operation is there which gives you again a third generator. I mean some generator in the same space. Okay? So this is a very important thing. So there is this is general feature. In all the groups that we'll be discussing, these continuous groups we'll be discussing, this is the general feature. There's a commutator structure on top of just a vector space, which is nice, but it doesn't give too much information. Yeah? But this commutation relation gives a lot of information, essentially all the information, and you will see. So this is a very important statement. So in general, so in this particular case, it was so the commutator was just that. Let me write it here. Sigma A, sigma B is equal to 2I epsilon A, B, C, sigma C. Okay. Sometimes it is convenient to remove this factor of 2, okay, and you'll see why it is useful. Although it's not necessary, there's nothing, but it's just convenient to redefine. So I can absorb it by taking sigma A by 2, sigma A by 2. Let me see also, maybe in the notes we have also absorbed the I. No, at the moment there is no I, is not absorbed. Take this. So if I look at this commutator, then what will I get? 1/2, so there's a 1/4, because this comes in sigma B. So, this is just a number, I can take it out, right? So then this gives you 2I. This with that gives you 2I epsilon ABC, sigma C. So this 2 makes it 2 here, and then put it back here. So if you call this as a generator, the basis for the generator, sigma polymatrices were just a basis, and we expanded arbitrary generator in terms of polymatrices, right? But suppose you had redefined your generators by multiplying by 1/2, then this coefficient of the commutator algebra is simply I times epsilon ABC. Okay? Sometimes, in particular in mathematics literature, they redefine also by absorbing I. You know, you can also absorb the I by, for example, multiplying by say minus I sigma A by 2 minus I sigma B by 2. So minus I times minus I gives you, so this is the same as minus 1/4 sigma A sigma B, but that's the same as minus 1/4 I times 2, I mean from here, epsilon ABC, sigma C, and now your 2 cancels, and then you absorb this inside here, sigma C. So you see this again, I can write it as minus I, sigma C. Okay. So now you see that this is simply epsilon ABC times minus I, sigma C. But in mathematics literature, somehow they prefer to use something like that. They prefer to use anti-Hermitian generators. Okay? Physicists always like to deal with the Hermitian generators, but they like to do that. And in that case, this coefficient, by the way, this coefficient, whatever basis you choose, of course you see that this coefficient changes, no? But in a trivial way, because that is simply a matter of change of basis. But apart from that, this is called the structure constants. There's a name for that. These are called structure constants. And we will see that essentially everything about almost most of the properties or the group, it can be understood by just knowing this structure constant. Okay. We'll see that. Of course, we'll see in SU2, but also in higher groups. Actually, this is the most important information. Okay, now five. So, are there any questions here? Because now I want to move to SO3.
Yes, actually, the equation sigma A over 2 plus sigma B over 2 is equal to 0 was 1/4.
Yeah, I mean, so yeah, so if you look at this here, if you compare this with this side here, right? So there's an extra 1/4.
Yes.
Now if you compare here, there's this again extra 1/4 because 2 divided by 4 is half. Yeah. I mean, yeah. So this is not important. Change of base is not important. Right? That's a trivial redefinition of structure constants. Okay. Now let's go to the SO3. I'll try to finish. I want to finish this chapter today here. How much is it? It's possible. Okay, so now we go to SO3. The reason why I'm discussing SO3 is we'll see that SO3 is almost the same as SO2, with a minor, not so minor, I mean, this can be important for some physical situations, but just one difference, essentially. So, SO3, so let's look at this group. So what is this group? Let's use the symbol that is used here. We call it M. So M, so suppose if M is an SO3, M is a matrix, 3 is a 3 by 3 orthogonal matrices with determinant equal to 1, right? Det equal to 1, because the S stands for always det. O stands for orthogonal, S stands for, so orthogonal here is O, and determinant equal to 1 condition is S, and 3 just means 3 by 3 matrices. So the conditions are M transpose, M transpose, it doesn't matter, either way doesn't matter. M transpose or M transpose M, it doesn't matter, but I will just follow the same notation. M transpose equal to 1, identity. So this means transpose. And also I will take it to be real. Okay? So all the entries in the matrix are real. And then transpose equal. And determinant condition, this determinant condition is simply determinant of M as well. Right. Now, I think we discussed already in general, we discussed SON in general, right? SON and ON. We discussed two lectures back. So, you see, first of all, this condition, just like in the SU2 case, we had SU2 case, we had a U dagger equal to 1, and then det U equal to 1, right? But then, already from this equation, we found that the determinant of U is just a phase, right? Now, let's look at here. This tells you that, I mean, if you look at the determinant of this equation, so take the determinant of this equation, det and M transpose. Determinant of identity is 1, so that's that. So this already implies that, right? This is not a new condition. If I found an M which satisfies this condition, this is automatically true, right? But this, determinant of product of matrices is the product of determinants for square matrices, and these are all square matrices. So you get here determinant of M times determinant of M transpose. But determinant of M transpose is the same as determinant of M, right? So this is the same as that, which means it's determinant of M squared. And that's equal to 1. That's equal to 1, that's the condition. So what we are saying is that once I have satisfied this condition, then we are guaranteed that determinant of M is either +1 or -1, right? Because we are discussing real matrices here. So it's a real matrix. Actually, in general, it's only +1 or -1. Even if it's a complex case, this is still +1 or -1. There are only two solutions to this equation. Now, so you see, here on the other hand, it was different. Because here, when you take determinant of U and U dagger, U times U dagger, that's the same as determinant of U times determinant of U dagger. But this is the complex conjugate of that. So we found that this is the modulus square of determinant of U. Okay. And so this is equal to 1. That is, this suppose I found a U which satisfies this, then Determinant of u satisfies this equation. But this still allows you to have a phase. Determinant of u could be some e to the power of I theta. Right? So that was the difference between that. So that is why you see in the U2, dimension of U2 was 1 bigger than SU2. Right? Because of this extra theta there. But here there is no continuous parameter there. Either you are +1 or -1. Okay? So suppose I found an m such that determinant was +1. Suppose I found m. Can I construct another matrix m whose determinant is -1? Well, I can just take m and replace it by -m. Right? Because if determinant of m is plus, if it was +1, then determinant of -m will be -1. Why? Because it's an odd 3 by 3 matrix. Right? I mean, in general, if it was an n by n matrix, then this would be -1 to the n times determinant of n. Right? But since n is 3, n is odd, this is simply -1 to the n, which is minus. So you get here minus in the case of interest. So it's not a big deal. I mean, if you found a solution for this part, for the +1, for the negative, you just have to multiply by minuses. It's nothing. There's no extra parameter. Unlike here. Here there was an extra parameter there, right? But here there is no extra parameter. That means, as far as computing the number of parameters is concerned, we can just focus on that equation. This doesn't give you any new conditions. The small, the parameters, but the continuous parameters are the ones which make small changes, no? Continuous changes. By continuous change, you cannot go from +1 to -1. Okay? By continuous change, you can go from 1 to e to the I theta by taking theta very small, right? But here, from +1, simply there is no way by a small change you can, and continuously change, you cannot reach there -1. So that is why it is enough to just, as far as counting the parameters is concerned, counting the dimension is concerned, it's enough to look at just this condition. This is enough. So how do we count this? Now, so first of all, M was a 3 by 3 matrix. So it had, and real. So M is 3 by 3. M is 3 by 3. So 1, 2, 3, and so 3 times 3. So there are 9 parameters, 9 real parameters, because we are talking about the SO3R. Right? Okay. Now, if you look at this equation, MM transpose, you see, okay, so let's look at MM transpose and try to understand whether this has some property, some special property. In fact, it has a property that if I take MM transpose and take the transpose of that. Okay. So this will be, when you take the transpose, the order changes. So it will be M transpose times M transpose, right? Which is the same as, I mean, transpose is the original matrix. So it is MM transpose. That means the left-hand side of this equation, so forget about the right side, no? Let's look at the left-hand side, is automatically symmetric matrix, right? So it's a 3 by 3 matrix which is symmetric. So what does it mean? It's MM transpose, if I look at the MM transpose in general, for any real matrix M, it is going to be something, some diagonal element, let's say x1, x2, x3, and then here you have x4, but it's symmetric, so this must be x4. If this is x5, then this must be x5. And if this is x6, this must be x6. Right? So there are only 6 independent quantities here. Because as I change this matrix M, change the parameters inside the matrix, this x1, I mean, these guys will change. But once these guys will change, this guy is not independent. This is given by that. Okay? So now if I want to set this condition equation, we have this equation. So how many equations I will get? I will get, of course, x1 equal to 1, x2 equal to 1, x3 equal to 1. x4 equal to 0, x5 equal to 0, x6 equal to 0. Okay? But this equal to 0 is automatically satisfied once I set this equal to 0. Right? That is because this is symmetric. So this is this is a general strategy. When you have some condition like this, you ask first, before looking at the right hand side, you ask the question, does this matrix have some special property? No? Okay, for the UU dagger case, this matrix was Hermitian. Right? So we knew that again, the number of equations are not the same as if it's an n by n matrix, you'll have n square complex numbers. So it is not the n square complex equations. There's much less equations because not all the n square components were independent. Same thing here. So that's the first step, and we see that there are 6 independent equations here. No? This equation, mm transpose equal to identity, has 6 independent equations. 6, why? Because 1, 2, 3, 4, 5, 6, and these are not independent. These are the same. So in general, if you had taken n by n matrix, suppose this was 3 by 3, but if I had taken n by n, then it will be n by n matrix, but symmetric matrix. So the number of equations will be, first of all, the diagonal ones, right? The diagonal ones are completely independent. So you get n, so this is coming from diagonal. Now the off-diagonal guys, total number of off-diagonal guys will be, so what is off-diagonal guys? Is n square minus n, right? The total number of elements is n square. I remove the diagonal, and so n square minus n. But what we are saying is that this and this are the same. So actually you have only half of that. Right? So these are so there are so many independent equations. And if you just add that up, what do you get? So you get here half n squared times n. So n times n plus 1. Okay? So that many equations are there. But the total number of parameters inside the n was n squared real numbers, right? So you have n square real variables, right? And this equation there are so many equations that these n square real variables have to satisfy. So how many variables will be left over after solving that? We are not solving them because they are, as we discussed, the nonlinear equations. So it's very difficult to solve. But we can at least count how many parameters are there. No?
N squared minus half n.
Sorry, repeat that again?
N squared subtracted from half n.
Exactly. So the total number was n squared. Exactly. So you have a total number of parameters in M is equal to n squared. The number of equations, number of independent equations is half n times n plus 1. So the number of free parameters after solving this equation, number of free parameters will be the difference. Will be equal to n squared minus half n times n plus 1, which is half n times n plus 1. In the particular case for n equal to 3, which is what we're interested in, for n equal to 3, 3 times 2 cancels, so this is 3. So this is the number of parameters is equal to 3. So the dimension of SO3 is 3. Okay. As I said, this equation, this determinant condition didn't play any role. So even if you had gone to O3, not SO3 but O3, where you don't impose this condition, still the number of parameters is 3. Unlike U2 versus SU2. SU2 had dimension 3 parameters, U2 had 4, right? So that doesn't happen because this condition is. Okay. So this is so SO3 is same dimension as SU2. So what we're seeing is that dimension of SO3 is the same as dimension of SU2. So then it's a natural question to ask, are they the same group, or is it, like we saw, SO2R was the same as U1. Remember? There, of course, both of them were one-dimensional, and we saw they were the same group. So we can ask also the same question. Are they the same group? Okay. And now, there is a very, so I'll go to the, I mean, there are several ways of seeing it, but we will, let's look at the group level first.
SO3 is abelian, right?
Not abelian. It's not abelian.
SO3?
Not abelian.
But
No, SO2 was abelian.
yeah, but SO3 is not abelian.
Not abelian, correct.
Actually, sorry, SO3 is abelian, right? Because it's the same as U1, I think.
No. What we saw before, I mean, that was a few lectures before, last week, right?
Yeah.
We saw that SO2, not SO3. SO2
Okay,
was the same as SO2R, was the same as U1. This was one-dimensional, and SO2 was also, SO2 was just a rotation in a plane, no? That's also, only one angle is there. So it's also one-dimensional. Both are one-dimensional. Now SO3, what is the interpretation of SO3? I think we discussed also that. It is basically, I mean, when you talk about SO3, when you give a, I mean, this is a 3 by 3 matrix, right? Whenever you see a matrix, you can always think about this matrix multiplying a column vector, no, of the same dimensionality. So if it's an n by n, you take an n column vector, and if you multiply m on this n column vector, you will again get an n column vector. So you can think of this m as a transformation on an n-dimensional vector space. No? When m acts on this vector, it gives you another vector. So it's some kind of a transformation on the vector. So in fact, it's a linear transformation also, right? Because if I take vector v1 plus v2, I mean, if m acting on v1 goes to v1 prime, and m acting on v2 gives you a v2 prime, right? Then m acting on v1 plus v2 gives you v1 prime plus v2 prime. So it's a linear action. So, so for the O2, it was natural to think of, these are 2 by 2 matrices. It's natural to think in terms of action on a two-dimensional plane, right? Since these are all real, so we want to think of a real vector space. So this 2 by 2 will act on a two-column vector with real entries, because these are all real. This SO2 is a 2 by 2 real. Okay? So you can think of it as action on this. So it transforms. It does something. I mean, if I have x, y here, it may go to something which is some combinations of some, let's say, call it x prime, y prime. Precisely what x prime, y prime will depend on the details of this matrix. Okay? But we know what it is. I mean, we have the intuition, I think, that this SO2 is doing nothing but the rotation in this two-dimensional space. But not an arbitrary rotation, because you see, this doesn't change the length of the vector, right? Because, so in a matrix notation, I can write it as n times x, let's say. There x is a two-column vector. This is a two-column vector. Right? Now, if you look at the length of the vector is nothing else but x transpose x in the matrix language, right? Because, I mean, you see, this is a two-column vector, that's a row vector, x, y, and the length square is simply x squared plus y squared. That multiplication gives you x squared plus y squared. So a convenient way of writing the length is nothing else but x transpose, length square is x transpose x. Right? This is a column vector, that's a row vector, so the result will be a number. No? Okay, now if I make a transformation, if x goes to mx, if x is replaced by mx, so this will go over to mx, and then the transpose of that, which is x transpose, m transpose. Right? Now if m is orthogonal, then m transpose is equal to identity. So this is identity, this is 1. So therefore, it's an x transpose x. So the interpretation of this transformation is a linear transformation which preserves the length of a vector. Okay. Same thing happens for SO3. SO3 is, what are we doing? Now it becomes 3 by 3. So this is now 3 by 3 matrix. And here you have X, Y, Z, let's say. X, Y, Z. But again, just think of this as a 3 by 3 matrix. This is the 3-column vector, right? SO3 also is a linear transformation on a 3-dimensional space, right? Which does not change the length. Okay. That is the point here. And by the way, what is the meaning of S? So SO3 is the rotations. All the rotations in 3 dimensions which preserve the length square. Okay? But it does not, I mean, there are other things which preserve the length square, but they are not rotations. Like, for example, parity. You just take a mirror image. That's not a rotation. And in fact, in O3, the elements that are there are precisely a rotation together with the parity transformations. But this is, SO3 is pure rotation, 3-dimensional rotation. And you know already from your study in particle mechanics and so on, that a 3-dimensional rotation can be parameterized in terms of 3 angles, the Euler angles. Those are the 3 parameters. I mean, of course, you can parameterize in many different ways. You know? I mean, for example, one convenient way, which for me, the convenient way to think about it is decide your axis of rotation, first of all. Choose your axis of rotation, right? Axis of rotation is a direction. So that specifying that, say, unit direction length vector, you need to specify 2 things. That angle, that line, so what angle theta and phi, the azimuthal and the other angles. Once you specify these 2 angles, that you specify uniquely the axis. But after having fixed the axis, you still have the freedom how much you want to rotate, right? So there are three angles there, 3 parameters. So it's just different ways of writing it, but the physics of it is just that. SO3 is a rotational symmetry in 3 dimensions. And as we'll see that the SO2 and SO3 are very closely related. So let me just quickly go through this one point here. And this is very explicit. I mean, this is a very, this part, please look at it very carefully. So let us go back to SU2 and consider the following thing. There is an action which is called the adjoint action. I mean, this is for any group you can define that. Any, not just SU2, SU3, all of them. I mean, any continuous group you can define that. So this is called. So what I have is I have the one thing I forgot to mention. We said the space of generators was a vector space, right? But we also noticed, we also realized that it has another very important property, that there is a commutation condition defined. So let me just write down a name. So this is called such spaces, such vector spaces which also carry a commutation relation are called Lie algebras. Okay, I am not defining now very precisely this. We will discuss it more precisely later. Okay, maybe the 7th chapter or 8th chapter we'll discuss that. The more precise definition. But for the moment, I just want to use this name. Instead of calling generators, I will just call them Lie algebra. So basically, it's a vector space which has a bracket structure. Okay, this is the commutator. You know this commutator X, Y was some Z. This commutator structure. Commutator of 2 generators was again a generator. That thing, right? So that commutator structure. This is called a Lie bracket structure. I mean, when I say I've not defined it properly, is because I have not given you all the definition, all the conditions that they should satisfy. Okay. That will be, I mean, this is anyway a group. SU2 is a group. So we know that all those conditions will be satisfied, which I'm going to define probably not even this week, next week. Right? What we'll do when we discuss it more generally the Lie groups and so on, more generally these groups, we will try to define in very general terms. Just like in the very first lecture, we define the groups in a very general term, right? The basic definition, what the group should satisfy. Associativity, existence of identity, existence of inverse, all those conditions. No? Similarly, we will define all the conditions that this bracket structure should satisfy. Okay? So that's why I'm postponing that discussion. But I will just use this word Lie algebra. This is a Lie algebra, but we will find the definition later. Okay, so Lie algebra, which means generators. For the moment, whenever I say Lie algebra, just think of it as generators. Lie algebra of SU2. Let's start with SU2. So this we saw are generated by Pauling matrices. If you want to deal with the Hermitian matrix, you use sigma A. If you want to use anti-Hermitian, you put an I there. Okay? Sometimes I keep changing, but I will specify when there's no change. I mean, there's no physics. There's no difference in that. Whether what basis you choose, you just have to keep track of it. Once you choose some basis, you have to stick with that. That's the. So let me just choose this basis, sigma A. Now there is an action. You see, there is this adjoint action. This is called adjoint action. Is a definition. Adjoint of adjoint action for every element G belonging to SU2, G is an element of SU2. I don't know if I was using this notation. Okay, and let's say so I can define an action which is I will call add for adjoint. Adjoint. The action, of course, will depend on G, which G you chose. I mean, it will act differently for each G. No? It will act on sigma A, okay, and it will give you something, okay. And what that something is, I'm just defining this: G inverse sigma A G. This is what's called the adjoint action. This is a definition at this stage. Okay. First of all, you want to ask the following question: when you say there is some action, add action on the space of generators, or space, or Lie algebra. Lie algebra, by that, for the moment, always think just a space of generators, because I have not defined properly. Should be, again, go to Lie algebra. Otherwise, I mean, it shouldn't be taking you out of that space, right? Otherwise, it's not a well-defined action. When I say there is some action on this Lie algebra, it means when it acts on the elements here, it gives you back again elements in the same space. Huh? Otherwise, of course, you can also consider situations where there are actions which takes you from one space to another space. But we are not considering that. We are considering an action which takes the Lie algebra to itself. Huh? If you take an element of Lie algebra, this action, there is some action which is defined by that, it should again be an element of the Lie algebra. So first question you can ask is that how can I be sure that this is in the Lie algebra? I mean, this is in the this is a generator. You know, how can I be sure about that? Okay. To check that, remember the generators of the SU2, generators of SU2. I have chosen a basis here, but generic generator of SU2. I'm using the Hermitian. Is all traceless Hermitian matrices. Traceless Hermitian 2 by 2 matrix. Hermitian or 2 by 2. 2 by 2 traceless Hermitian matrices. That's a definition, right? And we saw that sigma A provides a basis for that, because any such matrix I can expand in terms of sigma A, the 3 Pauling matrices. Okay. Now, so in order to show that this is again a generator, basically what we want to check is that these two properties, that this is Hermitian and it is traceless. These are the two conditions we need to check. If they satisfy, then we know that this is the generator. Right? So first let's look at the Hermeticity condition. So G inverse sigma A G, dagger. Let's take the dagger of that. When I take the dagger, it goes other way around. I mean, order changes. I open it up, the order changes. So it becomes G dagger sigma A dagger, and G inverse dagger. But in SU2, this belongs to SU2, we already know that G dagger G is equal to identity. Right? We already know that. So, okay, so this in particular means that G dagger is G inverse. Right? So this guy is simply G inverse. Sigma A, of course, is Hermitian, so sigma A dagger is sigma A. And G inverse is G dagger, but dagger, G dagger is G. Right? So you get back that. Okay? So you see that this is Hermitian. We got back again the same thing, right? Dagger of this is the same. So it's Hermitian. So this shows that it is Hermitian. The second condition we need to check is that it's a trace condition. So what about the trace? So let's just take the trace of that. So trace G inverse sigma AG. Well, a trace you can see, you can do cyclic. You can move it cyclically. So that's the same as trace G inverse sigma A. But G inverse is identity. So that's the same as trace of sigma A, which is 0. All the Pauli matrices were traceless. So this satisfies both the conditions. Therefore, I should always be able to expand it because this is a complete basis, right? Any such matrix I can expand it as a linear combination of these matrices, right? So, therefore, the conclusion is that this matrix, G inverse sigma AG, can be expanded again in terms of, and let me call it the coefficients. So let me write coefficient. Let me not use the m. Right? Actually, here is used m. So let me use the m b times sigma b. Okay, but you see, these coefficients will depend on. I mean, I could have chosen a different a, then these coefficients will change, right? I mean, when a equal to 1, for example, this will be some coefficients. I mean, what is guaranteed is this is going to be some linear combination, sum over b, with some coefficient. But that coefficients will depend on which a you chose, right? So to remember that this coefficient depends on a, I explicitly put the index a here. Okay? I put the index there. So these are numbers on this day. So because the fact that the numbers will depend on which a I chose, that information I'm keeping it here. And it will depend on something else also. It will depend on G. Because G is an arbitrary element of SU2. If I had chosen a different G, those coefficients will change. So I also remember that, I put here also that it is a function of G. Which point in the SU2, which element of the SU2 you are taking. It depends on that. So these coefficients depends on A. Of course, it depends on B because explicitly because the linear combination of sigma B, no, which are coefficient. And I keep this to remember that as I change G, this is also going to change. These coefficients are going to change. So we have this. So this is fine. So that's the coefficients. And furthermore, we know one thing. Because this is Hermitian, because we already saw this is Hermitian, this must be Hermitian, sigmas are Hermitian, so these coefficients must be real, right? So all of these coefficients are real. So now you can arrange these coefficients as a 3 by 3 matrix because A and B go from 1, 2, 3. So you can think of it as a 3 by 3 matrix with real coefficients. Okay? Now what we want to show is that this 3 by 3 matrix is in fact an SO3 matrix. Okay? So you will see now. So that's a very nice result actually. Sorry, before I erase, I should ask you any questions? I mean, you should also ask questions, you know. Nobody is asking any questions from here. Please ask. Whenever you just stop me, interrupt me, and don't hesitate to interrupt. So any questions on that?
Are we using the same n?
Sorry?
The matrix n? Are we using the same n?
No, at the moment, that's why maybe I should have used some other symbol. Let's call it something else. Let's call it some n. This is just a symbol, this is a notation, nothing more than that. So these are the numbers. So for a fixed a and a fixed g, there will be 3 numbers here, because it's going to be some combination of sigma b's. So there will be 3 numbers. But as I change a, so for a equal to 1, there will be a set of 3 numbers. For a equal to 2, there will be a set of 3 numbers. A equal to 3, there will be a set of 3 numbers. But those numbers, I arrange it in such a way that I think of it as a matrix. So let's say A is going along this direction and B is going along that direction. Actually, let me see. This is the notation. Oh, okay, I think this is the notation. So think of this A. I mean, it doesn't matter. Okay, for the moment, I'm just taking this. Think of this as A is labeling. So I arrange these numbers. So you see, for A equal to 1, I have 3 numbers. B equal to 2, I have 3 numbers. A equal to 3, I have 3 numbers. These 9 numbers, I'm arranging it in a matrix form. I mean, I'm free to do that. Right? I can just arrange it any way I want. So I arrange it as a 3 by 3 matrix. So here there will be, say, n11, n12. These are all depends on the G. n13, etc. n21, n21, n31, and so on. But also, one has to remember that these coefficients will depend on which G you chose, right? For example, if I had chosen G equal to 1, identity, then nothing. This will be just numbers will be delta AB, right? If suppose G was identity, nothing happens. Sigma A goes to sigma A. In that case, this will be just delta AB, no? But if I choose a different G, it will change, no? So these numbers will depend on what G you choose. So that information I'm trying to remember it by, so that I don't forget that it depends on the G. I keep that G explicitly there in the bracket. That is, it's a function of G. It depends on, each of these coefficient depends on G. Okay, now, so we want to, let's see, so we want to, so the statement that we want to prove, the statement is the following, that this matrix N is viewed this way, as a 3 by 3 matrix. So A in this, going this way. It doesn't matter whether you put A there and B here, it doesn't matter. Because after all, it will be a transpose. But the transpose will, if you show that this is SO3, then the transpose will also be part of SO3, right? So that doesn't matter. So let's choose any one of them. Okay, so we want to show that this 3 by 3 matrix of N here is SO3, is an SO3 matrix. This is an SO3 matrix. Okay, first thing, of course, as we said, these are all real numbers. So that agrees because SO3R. So that's fine. But what we need to check is that this is 2 conditions, that N transpose N equal to identity, and the determinant of N is 1. So let us start by the following thing. Let's just take this G inverse sigma AG and multiply it to again G inverse sigma BG. Okay. A and B are arbitrary. Arbitrary. Yeah? It could be the same or it could be different. Arbitrary. 1, 2, 3, 1, 2, 3. Huh? Okay. So what is this? Well, let's just use this part, this definition. So I will find. So I have 2 ways of writing it. So okay. So this is the same as G. I mean G inverse cancel. So you get here sigma A, sigma B. G. Okay. But sigma A, sigma B, we already know is, let's just simplify that, we already know is delta AB I, identity. You remember the polymatrix, I wrote down those polymatrix, this was sigma A, sigma B was delta AB times identity matrix, plus I, epsilon ABC, sigma C. Right? That formula which I wrote down before. I mean, we actually checked it also on the blackboard. So I'm just using that. So that's plus I, epsilon ABC, sigma C G. So what's that then? What I will do, the strategy is the following. So this is what I'm trying to compute, right? So one way to compute is by first do this and then manipulate that. Another way to just directly use this definition, okay, and go through a manipulation. But the two should be equal, so we'll get some equations. Okay, so let's open that up. Well, this is identity, so G inverse identity, G is identity again, right? And so first term is simply delta AB times identity. And the second term is plus I epsilon ABC. I mean, this is just a number, take it out. And then we have G inverse sigma C G. But now I use this equation here. Okay. So therefore this is delta AB identity. Now that is as it is. But here I write I epsilon ABC times N. So this is C here. So let's call it N CB sigma D. Okay. So here G inverse sigma AG was, where it's understood that when there's a repeated index, it's summed over. This convention is very much used in physics. Whenever you see a repeated index, it's understood that it is summed over in the appropriate range. It's summed over. Okay, and of course this depends on G. These coefficients depend on G. So that is one way. So this way of doing it, we get that answer. But now let's do the following. Let's just use this equation directly here. Okay. So this is one way of doing it. Now do it this way. What is this one? So G inverse sigma AG times G inverse sigma BG will be, directly use that. So it will be N A, now say, I don't know, E, let's say. I'm running out of indices. N A E sigma E, so there's again G sigma E. And here you get N B F, let's say, G sigma F. Okay? These are numbers. Okay, but these are the matrices are here. All these are numbers, which is the same as NAE is a number, NBF times sigma E sigma F, sigma E sigma F. Again, I use this equation here. So you get here delta EF times identity plus I epsilon EF A, B, C, D, E, F. The G I don't want to use because G is here. F K, let's say. G E F K, epsilon E F K sigma K. So we have two expressions for this the same quantity. One is this, and other is that. These two must be equal because after all we started from the same thing, here. So this is going to give us some equations, right? So first of all, notice that now we know that so here you see that you have identity matrix and the polymatrices, right? Here also you have identity matrix and the polymatrix. So since these are independent matrices, I mean identity and all the three polymatrices, they are independent matrices. So each of these terms must be related. I mean, must be equal. So the coefficient of identity, when you equate the coefficient of identity, what do you get? So there is a delta. So NAE, so there is a delta EF. So let me put here. So NBE is equal to delta AB. That's the first condition by looking at the identity matrix. So that's it. Now this is, if you think of a matrix here, so where A labels the column, row, and E labels the column, And so this again, I keep forgetting to write G. This depends on the G. So then this is nothing else but N transpose. Right? Because AEEB would have been the matrix multiplication, but you just take the transpose of that, so it's N transpose EB, right? So this is just a normal, this is a matrix product with the, and we're looking at the AB of this AB term of that, and we are saying this is delta AB. But that's the same as in the matrix language. This equation is the same as N transpose N transpose G is identical as a 3 by 3 matrix. Delta AB is just the identity of the 3 by 3 matrix. Okay? Right. So this is orthogonal, you see. So what this is saying is that this matrix N, viewed as a 3 by 3 matrix, where A labels the row and B labels the column, okay, is an orthogonal matrix, because this is exactly the condition of orthogonality. That's the first statement. Now the second thing, so, but from here, by equating, we have more, this is the information from the delta term, I mean identity term. Okay? Now we have many more conditions here by looking at the polymatrix. So to use this, what I need to do is to change the symbol here, D. Call it D. Okay? K is replaced by D. There was no other D appearing here. Okay? And now I can just look at the coefficient of sigma D on both sides and equate that, because they have to be equal. So from, oh, it's already 6. Well, let me at least try to finish this. You must be tired because today is the second 2 lectures, no? Okay, so if we let's equate that. So from this side we get here, okay, I is appearing on both sides, no? So I can forget about I. But what I can do is I can write epsilon A, B, this the remaining parts. So you have N C D. Okay, I will sometimes forget to write G, but it's understood that this matrix depends on G. That should be equal to, from here, you have, again, sigma D, so we have, I've removed both sides, so epsilon EFD times NAE and NBF. Is correct, and I hope I've not messed up with the indices. So this is the equation. Okay? There are 3 equations here because D, for each sigma D, there are 3 equations. Okay, so we already have proven that N is orthogonal, right? Now we want to actually check, I want to prove that this is determinism. Okay? So let's do the following. This is almost looks like a determinant if I put one more n, right? I mean, determinant of n has a formula, right? The determinant of n you can write, express it like this. So dit n is nothing else but epsilon, say A, B, C, and 1 A, and 2 B, and 3 C, right? That's the determinant of n. But what I can do, I can so I mean, ABC, you can also write it in a slightly different way. Yeah, if you take, so you can also write it like this. So A, let's say A, B, C, and then let's put something else here. Epsilon D, no D, this index will not be the same, but it doesn't matter. We'll check. E, D, E, F, let's say. Suppose I compute this. What is it going to be? It is going to be determinant n times epsilon D, E, F. Right? It is clear that it's going to be proportional to epsilon D, E, F. Right? Why? Because, I mean, if any of the two, if I exchange any of, say, E and D, here there's a summation over A, B, C. Right? and D, E, F are fixed. You fix your whatever value you want to choose. If any of these two indices are same, suppose D is equal to E, then it is going to be 0 because this is antisymmetric in A and B, right? So the result will be 0 if any of the two indices are equal, which is one of the properties of epsilon. If any of the two indices are equal, it vanishes, right? Secondly, also you see that it is antisymmetric in any exchange. It's antisymmetric in any exchange because if I exchange E with D, then it's the same as I can exchange B with A, but when I exchange B and A, I pick up a minus sign, right? So as a dependence on these free indices, D, E, F, this is a totally antisymmetric in D, E, and F. And there is only one such tensor, a third rank tensor exists, which is totally antisymmetric, and that is this Levi-Civita symbol, up to a number, up to a multiplicative factor. That multiplicative factor you can determine by just fixing it to be, say, 1, 2, 3. If I take 1, 2, 3, this is 1, and then we know it, that's a definition of determinant. So that's why this equation is there. It's just the same as what we had written before, except that now I have allowed it to be free indices. D, E, F are free. Before I fixed D, E, F to be 1, 2, 3. Now we can try to use this equation. This is very similar. I mean, E, F, I mean, here I could have exchanged, so it doesn't matter. I could have exchanged D, A, E, B, and F, C. So let's see. So okay, this is next. I want to write it in the same notation, same symbol. But okay, it doesn't matter. Let's see, E, F. So suppose I multiply this side by something which has the index D here, okay, and some index which does not appear here so far. Do you see any index which is not appearing? A, B, C, D, E, F, G, H, or K, let's say K. Right? So let me multiply both sides of this equation by NKD, okay, and sum over D. Okay. So I had this equation. Again, logic is this. I have this equation. This should be true for everything. So in particular, if this is true, let me multiply this equation by NKD, okay, and sum over D. Then it should also be true, right? So what I do is I multiply by NKD and sum over D. So in other words, since D is already appearing here, this is again the same convention. Anytime you see a repeated index, it is summed over. Okay? I mean, already I have not written some of the sums. No? C is repeated here. So C is understood that it is summed over. Similarly here, see what is E and F are summed over because that's repeated. So now I multiply by NKD and sum over D. So it's again understood that D is repeated index, D is summed over. Okay? Now look at this equation. Here, this is nothing else but the determinant. You see, this is exactly that expression. The, epsilon with the EFD being EFD. So this is going to be equal to epsilon ABK times determinant of it. Right hand side. What about left hand side? If you look at this here, epsilon ABC, yeah, look at that. I mean, so these are free at the moment. Yeah, just look at this part. So this is all G. Again, I keep forgetting to write G. If you look at this equation, D is summed over. I mean, this part. But this I can write as N CD and transpose DK. Transpose, sorry, not direct, transpose. But then it's just a normal matrix multiplication. So this object, this part, is nothing else but N and transpose. And we are looking at the element CK. Right? I mean, when I sum, because I remember I have to sum over D. All I did was I just rewrote that as N transpose DK. And now when I sum over D, that is nothing else but the matrix multiplication of N with the N transpose. Right? But after a matrix multiplication, it will give you the element CK. So that's what this function is. But we've already shown that NN transpose is identity. Okay? So this is delta CK. Okay? So this whole thing, therefore, is simply delta CK. Okay? So now delta CK summed over C, this just makes this index K. So it becomes epsilon ABK, right? Epsilon ABK times 1. Huh? And here it's again epsilon ABK times determinant of N. This should be equal. So that implies that determinant of N equal to 1. So it's quite amazing. See, what we, in our original definition, it was simply the statement G inverse sigma AG, that is how we started it, is going to be some linear combination of sigmas, because we know it's again in the generator, is a generator, Hermitian and traceless. So I just expanded it in terms of some matrix, some coefficients times sigma b, right? These are just coefficients. So there is summation over b, but b, that summation is understood. Coefficient, it depends on a and g. But then I just decided to rewrite these coefficients as arrange them as a 3 by 3 matrix. And then we find that this matrix, so this n is now, the A is going here, say B is going there. So this is a 3 by 3 matrix. And we find that this matrix is orthogonal and determinant equal to 1. So this shows that for every G, there's a G here, everything is G. So dit, got it right, dit N, dit N, did they write that? Dit NG. Right? So we are saying that this is equal to 1 and determinant of NG equal to 1. For every G, we have a matrix, 3 by 3 matrix, which is orthogonal matrix. So what we are saying that for every G, we are associating an SO3 matrix. Right? So this is a map from SU2 to SO3. But it is not, two of the SU2 elements go to the same N matrix. That is clear because, remember, if G is an element of SU2, minus G is also an element of SU2. Right? If we just replace G by minus G, nothing happens because this also becomes minus G inverse. So minus minus cancels. Okay? So this is a map from SU2 to SO3. What we have defined here is a map from SU2 to SO3. Map just means that for every element, I am associating an element here. Every element here is associated with some element there. But it is not one way, it's not just one element is mapped there. Two of the elements are mapped the same way. Because G and minus G, both are mapped to the same N. Same NG. In other words, N of G is the same as N minus G. So it's a 2 to 1 map. At least we know it's 2 to 1 map. It turns out to be true actually. We certainly know that G and minus G, just from the fact that it's quadratic. This is quadratic in G, so minus minus will cancel. Okay. It turns out to be that will be the case. Now there's an exercise here to show the other way around. You see, if I give you an arbitrary SO3 matrix, could I construct a corresponding G? That is important because if you look at this map, what are we? Then I will stop. Just one. If you look at it, SU2 is some space. SU2 is S3. So SU2 is some space. Let me just write it like that. This is SU2. And this is S3, but I'm just drawing. Is some space. And SO3 is something here. What we have shown here is that every point is mapped to some point here. Right? Because for every G, I can construct this N. I'm giving a constructive way. I'm giving a method to construct a 3 by 3 matrix.
G is an element of SU2.
Huh?
G and G minus 1 are elements of SU2.
Sorry, G?
G are an element of SU2.
G is an element of SU2, yeah. Yeah. I mean, that we use already. Remember, in order to say that this is going to be a linear combination of polymatrices, again, I've used already that. Yeah. So this is this SU2. This was what we were calling add action, add G action. No? Add G for okay. So for every element of SU2, I am associating a 3 by 3 orthogonal matrix with determinant 1, which means an element of SO3. So all of this space is mapped there. It's not a one-to-one map because G and minus G are mapped to the same point here. No? They're mapped to the same point. But we don't know, maybe it doesn't cover the entire SO3. Maybe this way, I mean, for each G I construct, maybe the image of this map is some subset of SO3. No? It could happen, no? We don't know yet. We have constructed some SO3, but how do we know that I can construct the most general SO3 matrix? This way, that we'll be able to reproduce the most general SO3 matrix. No? This depends on G. And as I change the G, maybe I cover the whole thing or not. We don't know. So the exercise problem that is given here is to show that that every element of SO3 is obtained as a map. That this is by the way, this is called the image of the map. So I have this space, I have mapped it to SO3. But it will be contained in SO3, but that's the image. Image need not be equal to the full space. It need not be in general. But what the exercise problem is saying is that in fact what you want to prove is that the image is in fact equal to SO3. The full SO3 is covered. Try that. Although I think, yeah, maybe actually the exercise 5.6 is also written. Don't do this one yet. Okay. So maybe wait. Don't try that because it's probably a little difficult. Okay, let's stop now here. So I'm sorry I took a long time. In fact, still I have not completed this chapter. No? I have to, but I think I did first 15 minutes. First 15 minutes of tomorrow I should be able to finish this. Okay. There was no question from you this time. I hope you were able to listen to all this, and maybe the connection problem, I don't know.
We can listen, but the problem is I think we should plan a room and dashboard doesn't look I cannot recognize all the work we need to do. I cannot recognize I have to do, so I'm gonna be close a bit. I'm doing it, I think I can do it. I'm gonna find the right answer.
Okay, good. So then we'll see you tomorrow. Tomorrow we'll meet. Okay? Yeah. Bye-bye.